Hello, and welcome to Backer Breaks It Down. In today's episode, we are going to investigate the short-run behavior of rational functions. Okay, so we've already discussed long-run behavior. We're going to focus on short-run behavior here. Maybe I'll throw some long-run in there just for fun. And so for short-run behavior, we're going to talk about like vertical asymptotes, X-intercepts, the Y-intercept, and something called a hole, which is exactly what it sounds like. Okay, so as you know, rational functions are quotients of polynomial functions. Okay, and since they are a fraction, that denominator, okay, whatever's in the denominator can't be equal to 0. Because if it is equal to 0, then like it's undefined. So that brings us to the domain of a rational function. So the domain of a rational function is the set of all real numbers except the x values that make the denominator 0. So that's something we have to think about when we're like considering what the domain of a function is like what makes the denominator equal to 0. Okay. Vertical asymptotes. So a vertical asymptote of a function is a vertical line, and we write vertical lines as x equals a number that the graph of the function approaches but does not cross. Okay. Now, in a rational function, it's possible that they have no vertical asymptotes, although that's kind of unusual. It's possible for them to only have one, like that's very common. It's even possible for them to have several vertical asymptotes. Okay, but I think this is like most commonly what you're going to see is one vertical asymptote. And if you think about it, like the vertical asymptote is just like one location where like graph of a rational function has nothing going on. So like we're definitely going to utilize vertical asymptotes to help us like determine domain because the function will be undefined there at the vertical asymptote. And so I had you investigate a bunch of graphs, like just check them out and make some connections. And so like basically I have two examples here. And like when I look at the graph, it's like, oh, there is a vertical asymptote right here at x equals -4. And when I look at my function, I see like x minus 4, right? Like where else in my function could they be getting this -4 from? Okay. And so it says here that vertical asymptotes occur at zeros of the denominator that are not also zeros of the numerator. Okay, so we're talking like x plus 4 in this function here is only in the denominator. So if I'm like, where does this equal 0? That's where I'm getting -4 from. It's where the denominator equals 0. Looking at the function on the right, like I see in the graph, like I see with my own two eyes that there is two vertical asymptotes. Like there's one at x equals -3, and then there's another one at x equals +3. And I noticed that in the denominator of the function are two factors that would totally tell me that. Okay, so zeros of the denominator that are not also zeros of the numerator. I know what you're thinking. What are those, right? So if I have like a common factor on top and on the bottom, what is that? That's a hole. Okay. So there is a hole in the graph and not a vertical asymptote if you have a common factor. Okay. So that's why it says it occurs at zeros of the denominator that are also zeros of the numerator, or more easily put, it's the 0 of the common factor. So in this example here, once I took my function and I wrote it in factored form, I noticed that there's a common factor of x plus 1 on top and on the bottom. And look, if you look at the graph, yikes, sorry about that. Okay, there's a hole in my graph, and the hole is located at an x value of -1. Sorry, I don't know why my computer does this. An x value of -1. And I can also see that the y coordinate's -2. So you might be wondering, like, where are they getting that -2 from? Because, like, clearly I can see where they're getting the -1 from. Because if I take x plus 1 and I set it equal to 0, I get -1. Okay. But as far as the -2 goes, like, that's what I'm seeing in my graph. It says right here that I can find the y coordinate of the hole by plugging the x value of the hole into the simplified form of the rational function, okay? So it's the simplified form they speak of. So if I look at my factored form, okay, right here is my factored form. If I actually take out those common factors, what I'm left with is 2 times the quantity x minus 1 on top. And on the bottom, I have x plus 3. And this is the simplified form, okay? Now, if I were to take my x coordinate, remember I know that x is -1, right? And if I were to plug that in, I know it's kind of messy, so I'm going to write it on the left-hand side over here. So now on top, I have 2 times the quantity of -1 minus 1 divided by -1 plus 3. So if I do the math, I'm going to get -4 on top and 2 on the bottom, and that is -2. And that is where they're getting the y coordinate from. Okay, so this like kind of analyzes quite a bit, all right? So this is like what we know. First off, like this y-intercept, every single time I talk to you guys about a y-intercept, I tell you there's one rule that fits everything. We need just to evaluate the function at 0. So like seriously, plug in 0 for x, calculate. They're indicating if you did that here, you'd get -15 over -10. Okay, that's how we find the y-intercept. We write our function in factored form because the factored form is going to tell us a lot. Okay, if we have a common factor, don't know why it's doing that, a common factor. So here we have -5 on top and -5 on the bottom. That tells me that there is a hole in the graph. And if I take the common factor and I set it equal to 0, like I can totally do this in my head, I can determine that the hole is located at x equals 5. Okay. What's left over on the bottom? Okay, so they're indicating that what's left over on the bottom is a vertical asymptote. So notice they're saying the vertical asymptote is at x equals -2, and boom, there it is. Okay. As far as the leftovers on top, they're saying there's a root at -1. So that's your x-intercept. Okay. So every little piece of this function tells us a story about its graph. It's kind of remarkable. I mean, if you thought it was kind of remarkable what polynomial functions were telling us about their graphs, this is even better, okay? So to just kind of take a look at some more examples, okay? So here we have the function g of x. Some things that I know about this function right off the bat is I can use that comparison test. And since the degree of my numerator is less than the degree of my denominator, what I know is that there is a horizontal asymptote at y equals 0. Okay, and if you look at the graph, it supports that. I can do the whole like plug in 0 for x. And when I plug in 0 for x, I get 3 on top and negative 9 on the bottom. Okay, I'm going to draw a big arrow here. Okay, and so that's telling me what the y-intercept of my function is, right? Because when x is 0, I get negative 3/9, which is negative 1/3, right? And that's where the y-intercept is. At that point, that's when I should factor. And I should write the numerator in factored form, and I should write the denominator in factored form, because I'm going to get a lot of information from this. The fact that I have a common factor here, right, x plus 3, tells me that there is a whole, because anytime I have a common factor, there is a whole. Okay. Once I cancel out my common factor, I can rewrite this like reduced function. And the reduced function is going to tell me a little bit more about my rational function. Like I'm going to use the reduced function to find the y-coordinate of the whole. Okay, so since I know the whole is at x equals negative 3, I can plug it into the reduced function. That's what they're showing right here. And I can calculate the value of my y-coordinate. Okay. Furthermore, the leftovers, meaning the reduced function, will tell me like where I have a vertical asymptote. So since in the denominator of x minus 3, I have a vertical asymptote at 3. And then there's like really nothing going on in the numerator, which means there's no x-intercepts. Okay, so every little piece of these functions tells us about their graphs, which is good considering like there's so many different graphs of rational functions out there. It's insane, right? Okay. So the x-intercepts, I already mentioned this. It's all about the leftovers in the numerator. So notice like here, I can see the x-intercept on my graph is negative 3. I'm sorry, it's positive 3. And the factor x minus 3 supports x. I'd be like, where does this equal 0? Well, it equals 0 at 3. And so that's my x-intercept. In the second function, I have 2 x-intercepts because that's like totally possible. Because x plus 2 tells me there's an x-intercept at negative 2. And x minus 2 tells me there's an x-intercept at positive 2. And then the wholes, this is just another example of a whole. And this one also takes into consideration like the x-intercept and the vertical asymptote. So you'll notice looking at my factored form, I have highlighted x plus 1. So that means there's a whole at negative 1. And then I'm saying that the x minus 1 on top indicates that the x-intercept is positive 1. Okay, so basically it's the remaining factors in the numerator that identify the x-intercepts. Okay. And so like you have this entire process outlined for you in like a logical manner of how you can fully analyze a rational function. Like before you do any factoring, compare the degrees of the numerator and the denominator to find your horizontal asymptote. Then find your y-intercept, plug in 0 for x and calculate. Once you've done those two things, then you can factor the numerator and the denominator. You can identify the domain by like asking yourself, where does the denominator equal 0? And then you can cancel out any common factors and write that reduced function. If you have any common factors, that indicates there's a hole in the graph. Plug the x-coordinate into like the reduced function to get the y-coordinate of the hole. look at the reduced function when it comes to vertical asymptotes and x-intercepts, because the vertical asymptotes are going to be the zeros of the remaining factors in the denominator. So we're talking about what's in the reduced function. And the x-intercepts are going to be the zeros of the remaining factors in the numerator. So what's in the reduced function? Okay. Just take it step by step, and eventually these are going to become like really easy. It's just at first it's kind of intimidating because, well, there's 8 steps here, right? So this is another like example that you have like in your notes, that once you're done with this video, go and look at it and make connections between the given function and those 8 steps, okay? So you understand what the original function in its standard form is telling us, what information we can get from the factored form, and then what information we get from that reduced function, okay? But until you become fully comfortable with all of this, use this guide, okay? Go through these 8 steps in this order, because that's the most logical way of analyzing these problems, okay? And that's how Backer breaks it down. We'll graph tomorrow. Got it? Bye.